So I will continue where we stopped before the break. I just went briefly through the structure of the boundary layer during typical daytime heat, where the surface is heated by the sun, and during nighttime. And I'll show you the radiation budget. This is one day, and this is the energy flux. And here the red curve shows us the solar energy, solar radiation coming downwards. Here is sunrise and sunset. This represents the reflection of the sunlight upwards, and the green line is showing us the radiation that comes from the atmosphere, which is actually substantial compared to the sunlight, at least in some places where the atmosphere is warm. And it's working in the night and in the day, but it has a maximum when the atmosphere is the temperature of the atmosphere is at maximum in the afternoon. The upward going long wave radiation is shown here, and in this case it is, as in most cases, it is substantially greater than the downward component. The position of these curves depends, of course, a lot on where you are on the surface. But in this case, the sum of all is given here as a black line. I remember when I saw this for the first time, I was sitting in minus 10 degrees and there was snow all over the ground, and it looked very, very wrong to me. This was very, very small, and these were quite different too. Now, the energy that reaches down goes either into warming up the atmosphere, giving more sensible heat, or to evaporation. And here we see different curves representing these two. That, of course, depends mostly upon the surface. In the desert, it goes into heating the atmosphere directly. Over the ocean, there's a lot of evaporation taking up the energy, and some of it goes into heating up the ground. Now, I'll say a few words about aerosols. Aerosols are, the science of aerosols is really gaining momentum in these years. And this has several reasons. Of course, pollution is related to aerosols, but this is one of the greatest sources of errors in climate modeling. Not only the direct impact of aerosols on the radiation budget, but the impact of aerosols on creation of clouds. There are many sources of aerosols. Some of them come from the ocean when the wind blows and the sea spray brings aerosols into the atmosphere. We have volcanoes, of course, intermittent, and then we have the deserts, which create a lot of aerosols, dust coming into the air, and we have different land masses that give aerosols, and of course industry and human activities. In the microphysical world, we have phenomena that are of very different size, which we tend to refer to all more or less as microphysics. We have extremely small aerosols, particles, up to quite big, that we call dust, and they are important for activating droplets and the growth of cloud droplets, which again later accumulate into raindrops. This is a raindrop. This is large aerosol particles, and this is cloud droplet. Typical. We tend to distinguish between cloud condensation nuclei aerosol and freezing aerosol, and the freezing aerosol is sometimes lacking for creation of precipitation, a limiting factor. And modern technique allows us to measure the optical thickness, the aerosolness in the atmosphere, and this is an example of aerosol from May 2010 from satellite, and we see that we get a lot from the desert areas and relatively little from most other areas in the world. Now I'm going to spend a few minutes on dynamics of the atmosphere. Dynamics on the atmosphere. There are many theories, long extended books on the forces of the atmosphere and how they give rise to winds of different scales in time and space. But let me first start with explaining this equation, which is perhaps the most simple and nicest equation that we have. We have a connection between pressure, temperature, and density, and sometimes or very often we take one of these variables, keep it constant, and then we consider transfer of energy between the two others. Of course, this equation of state is used in all sorts of scientific disciplines. The pressure, atmospheric pressure, is in short the sum of the mass of a column of air, and if you have two similar columns with the same temperature, same density, we have same pressure on both sides. However, if we I think we should maybe change computer for the next presentation. If we warm up one of the column compared to this one, we cannot deduct very simply that increased temperature gives increased pressure. The atmosphere is more complicated than that, and that is represented by this cross-section through the lower part of the troposphere, where we have cold columns. We have short distances between the upper level pressure levels and pressure levels close to the surface, while a warm increased temperature increases the distance between these two pressure levels. And we see that at the surface we have a low here and a high here, while at 500 millibars from hectopascals we have a high here above the warm air and a low above the cold dome. In dynamic meteorology, a typical way to go to understand processes is to pick out a few of the terms in the equations and neglect the others, or in other words, find arguments to set them equal to 0. And the most simple exercise is to take the gravity and the vertical pressure, and when we do that we get the so-called hydrostatic equilibrium. which is widely used in not only meteorology but in fluid mechanics in general. We can take two other terms, the horizontal pressure gradient and the Coriolis force. And then if we neglect all the others, here is the horizontal gradient. Typically in windstorms, mid-latitude windstorms, we get like 40 millibars for every 1,000 kilometers. Of course, there can be much stronger gradients and, of course, much weaker. The pressure gradient forces on a horizontal level, they point from a high to lower pressures. And the Coriolis force is quite a unique thing in terms that it's not a real force, it's a force that arises because of the rotation of the Earth. And the more you think about the Coriolis force, the less you understand. Mathematically, it is a force that pulls in the direction to the right of a movement of a particle on the northern hemisphere, to the left on the southern hemisphere. And we have all sorts of stories to try to explain the Coriolis force, but most of these stories have some drawbacks. They are not entirely physically correct, but so I will not tell these stories, but we just think of the Coriolis force as a force pulling us to the right or to the left as a function of latitude and wind speed. And the most commonly used balance in meteorology, of course mainly in the mid-latitudes, but also when you go a little bit away from equator, where the horizontal part of the Coriolis force is 0, is of course the geostrophic balance. And when we look at winds, these are winds at 300 millibars above the North Atlantic. These winds are quite close to being geostrophic in most places. But if we look, for instance, here, we see that there is a substantial ageostrophic part. A part of the wind is not geostrophic, and this part of the wind is contributing to moving the pattern to the east or to the west or wherever it's moving. But if we take, for instance, here, we can see that the wind is parallel to the isobars, and where the isobars are very dense, the wind is strong, but where there's greater distance between the isobars and where we move away from equator, you get weaker winds. Here we have these the Coriolis forces and the two horizontal directions and the pressure gradients in the same horizontal directions. We have frictional terms, which are, as I said before, they are usually in our models represented by, they go through the Reynolds averaging and represented by turbulent flow in the atmosphere. And they contribute to moving to changing the wind direction, of course, reducing the speed of the wind close to the ground, but the wind direction is changed. It's not geostrophic. The wind is blowing in towards lower pressure and away from higher pressure. the models we are running, they see all this. And these are the things that are well represented in the models. We can see that these are winds at 10 meters above the ground, and they are superimposed on the surface pressure pattern. And we can see that that the winds are blowing into the lows, especially here. The winds there's an angle between the stream where the surface isobar and the winds. We also see that the winds above land are substantially weaker for the same gradient as over sea, and that's basically because of greater surface friction. So I think that I stop here. I will continue some last part of this talk in my talk tomorrow, and I give the word to the next speaker. Thank you.